The last of our sequence-orientated videos is going to be talking about a fact that's very useful to us in a wide variety of circumstances. Suppose that you have a sequence and it is both bounded and monotone. It turns out if that's true, then the sequence automatically converges to something. For simplicity, I'm going to look at the situation where my sequence is bounded and strictly monotone increasing. You can do other types of arguments in a similar way for the other different possibilities. The bounded part just means that there's a pair of numbers, alpha and beta, so that if I look at the interval that starts at x equal alpha and ends at x equal beta, all of the a numbers are between alpha and beta. There is a closed interval that contains all of my sequence terms. Strictly monotone increasing means that if I make the index on the sequence terms larger, then the sequence term itself becomes larger. So A1 might be here, A2 might be here, A3 there, and even though the way I've got it drawn, the A numbers are rapidly approaching some value near here, each one is larger than the previous one was. Alpha to beta is an interval that contains all of the A numbers, but it may be a loose fit. It could be that beta is considerably bigger than any of these A numbers or any number that those A numbers are close to. It's conceivable that I could make beta smaller and still have an interval that contains all of the A numbers. It's conceivable that I could make it smaller than that, but I cannot continue moving the right end of my interval to the left forever because I'll eventually encounter some of the A numbers. A reasonable thought is that out of all possible right-hand ends of an interval that contain the sequence, there must be a smallest one. This number L, the smallest of all possible right ends of containing intervals, is often called the least upper bound. It's the smallest number so that all of the AIs are less than or equal to L. The key to the argument that I'm about to make is this. Let epsilon be a positive number. We usually think of it as being small, but just a positive number. Then I'm going to sit at the right end of my interval at x equal L, and I'm going to move to the left by the small positive amount, epsilon. Here's the key point. I claim there has to be at least one of the A numbers between L minus epsilon and L. The reason for that is easy enough to see. If this were not true, there would be no A numbers between L minus epsilon and L. All of the A numbers are less than L, and if none of them are between L minus epsilon and L, they must actually all be less than or equal to L minus epsilon. That means that L minus epsilon is an upper bound for the sequence. But L was the smallest upper bound. L minus epsilon is smaller than L is. So what we've found is an upper bound that is smaller than the smallest upper bound, and this is a logical contradiction. So the thought that I can back up a little bit and have none of the A numbers in this region is wrong. What we have figured out is this. If you give me a number epsilon that is positive, regardless of how small it is, there is at least one of the A numbers between L minus epsilon and L. There is at least one of the A numbers that is within distance epsilon of L. But on the other hand, if I know that my sequence is strictly monotone increasing, then the next of the A numbers, A number n plus 1, must be to the right of A number n, but to the left of L. That distance between L and A number n plus 1 is even smaller than the distance from L to AN, which was no more than epsilon. If you look at the next one after that, A number n plus 2 is to the right of A number n plus 1. The distance between L and A number n plus 2 on the number line is smaller than epsilon, and obviously this is always going to be the case. So in formal language, what we've figured out is, given a positive number epsilon, there is an index capital N, so that if I is bigger than that index capital N, the distance between A number I and L is less than epsilon. At first, this seems like it's kind of just a bunch of gibberish, but this was the formal definition for something that we have seen previously. This is the official formulation we had for the statement that the limit as the index tends to infinity of A number some index equals L. So if I have a sequence of numbers that is bounded and strictly monotone increasing, that sequence of numbers converges to something. As I said earlier, you can make similar arguments if the sequence is monotone decreasing, or if sometimes instead of strictly less than, you have less than or equal. All of these arguments follow the same basic pattern, though. So this is going to be a useful fact to us. A bounded monotone sequence automatically converges. This is all I wanted to say in this one. Starting with our next discussion, we'll think of having what are called infinite series. Until then, I hope everyone is having a good day, and I'll talk to you again soon. Language. If you give me a number epsilon that's positive, then there is an index which I'll call capital A.